Welcome everybody to this afternoon session of the workshop on modeling and control of the COVID outbreak. We start today with the keynote speech of Professor Munther Dahleh from MIT. Okay, so thank you, Munther, Munther has been working with his group on this, and I've been following his studies, and I think he is the best person to provide a view. And the title, I say, is really inspiring, because this is exactly what all of us has been thinking in these days. So how can we go back? How can we afford the so-called, what in Italy we call phase 2? So, and the title is Inching Back to Normal After COVID-19 Lockdown, Quantification of Interventions. So, inching, I think, is the right word.
Sorry, Fabrizio, do you intend to record this? Because it doesn't show on the screen.
Okay. I pause the recording, you're right. Thank you, Bob. Yeah. Okay, I give the word to Munther.
Well, thank you so much, Fabrizio, for the invitation, and it's very nice to see a lot of familiar faces all around the world. This is a new forum that's working really well. If I may, can I share my screen?
Yes, please.
Okay. Do you see my cursor as well?
Yes.
Okay, perfect. Okay. So I will give you an overview of the activities that our ISOLAT group at IDSS has been working on. This is a voluntary group that formed about 5 weeks ago, comprising faculty, research scientists, postdoc students, to be helpful to the broader community that we have in Boston and Cambridge about policy, interpretation of data, and so forth, and to think also with MIT about how we reopen MIT and how we reopen our society. We're about 25 people in the group. There are regulars, and these are the names, and all the credit of everything that I'm describing today goes to this group in various capacity. Please visit the website for details, and there's a lot more details on the website and explanation, and also contact information in case there's something you don't believe. I want to start with a caveat by saying that this is really not in the spirit of the research that we do all the time. So some of the stuff is just off the oven, so to speak, and I think we invite the whole community to join us on the ISOLAT website and vet the results and give us some feedback and ideas. But I'm indebted to this group, has been working really hard in the last several weeks. So just quick facts about the COVID-19. I think a lot of these facts are well known to many of you. There's been more than 2.5 million positive cases as of 2 days ago, and more than 178,000 deaths in the world. It appears to be a slightly different virus than the one we're familiar with as the flu virus. Its incubation period is longer. It seems to, for people react to it differently in different age groups. And as of today, infection testing is ramping, but it's not there yet. We don't have the exact numbers. We're not able to test as many people as we'd like to test. Antibody testing is still not clear. You know, there's a lot of work that is ongoing in antibody testing, but we are hearing different kind of reports in terms of its accuracy and in terms of its false positives and false negatives and what have you. And I think the objective that I've been hearing that has been reiterated over and over is how can we manage the number of infections, in particular as we unlock the lockdown and we go back to some sort of a normal life. How do we make sure that we don't have a peak in the reinfection? So these are the issues that sort of been kind of in our minds. And sorry. So the first thing that I want to my talk is divided into 3 components, and the first one I want to talk about is the data itself. And I think that this has been a topic of conversation everywhere, including CNN and so forth. Data is really noisy. So is it useful? And I want to make the point here that, in fact, the data is always useful, even if it's noisy, and it's important that we kind of remember that. So let me just kind of quickly go over that subject, and as I said, this is laid out in detail on our website. So first of all, we're looking into distinguishing two different scenarios. The first scenario is the one in the picture on the left, which represents a community where there was strict physical distancing involved in their strategy right from the beginning. And as a result, you see an infection curve, the black curve over here, that looks like a sort of a sub-exponential growth. And if you look at the logarithm of n of t plus 1 divided by nt, that behaves like a minus bt, where b is a positive quantity. So log nt over n is something, a curve that looks like this. This is an indication of a sub-exponential growth, okay, which is a result of probably a strong policy in terms of separation and physical distance. The community on the right is one where potentially had a strong growth initially, but then employed soft intervention and had another exponential growth, but there is no sub-exponential. So there's no flattening of the curve. So you see two exponentials over here, and in the log n over n, nt plus 1 over n, there's one exponential, and then maybe it dropped, but there is no sub-exponential growth, okay? And in general, what we're interested in is, by looking at the noisy data that we have, to detect whether the curve has flattened or the curve continues to grow, and that has very strong implications to policy, at least in the short-term horizon. Now, the gold standard in statistics, and what we all would like to do, is to get randomized testing of everybody. Okay, so even 5 or 10% randomized testing of the population will give us a fairly good estimate of the black curve over here, which will allow us to estimate the sub-exponential growth. And that's a statistical argument over there. And by the way, I'm dividing the community here to the infected people. Of course, we measure everybody, and then we see how many people are infected. Typically, infected people are either asymptomatic or mild or severe, and so that actually, in the random testing, it doesn't matter. You just test people and see what you get. The situation we have is not as good because this is scenario 2. So scenario 1 was the randomized testing. Scenario 2 is limited testing, which is what we have the situation in the United States. So what is the limited testing? Well, basically what happens is that people who have flu-like symptoms of some severe reaction go to the hospitals, they pass a certain criteria, and then they get tested. And so the only group of people that are getting tested are in the severe group over here. We don't have a picture of the people that are being infected, but are either mild or asymptomatic. And so as a result, this data is not indicative of the total number of people with infection, which has actually eluded us in terms of expectation of how many people are infected, what's the percentage of, what's the R naught, and so forth. And I'll come back to that in a minute. But with the, we have to make some assumptions as we analyze the data. And the one assumption we made in a lot of the work that we've done over here is that the fraction of people that have a severe response to the virus is a constant fraction of the total number of people that are infected. And it's not an unreasonable assumption to make. So, in fact, if you're able to drill deeper in the data and stratify it in terms of demographics, so for example, looking at the group of age, of older age and middle age and so forth, you can actually get this fraction differently in this group, and you can actually estimate the growth rate. The bottom line is that the ratio of nt plus 1 over nt is not affected by that fraction, and you still are able to estimate the growth rate independent of whether or not you actually have the full population or a sample of the severe population. So that actually makes us feel a little bit better on some of the things we estimate. So we can estimate whether or not within the sub-exponential regime, we can probably estimate the apex or the peak value, but we cannot estimate the actual numbers because the actual numbers are not available in these data. Okay, so based on this, and by the way, very quickly, I would say that the United States fits the scenario 2. we're not in scenario one, we're not doing randomized testing at all, and one can do a statistical test on the data, which I will not go through, that will verify that. So the first question that we asked is the curve flattening? And can we do a statistical test on flattening the curve? Now, this is statistics 101, essentially. What you want to do is do a hypothesis test. So your model is this logarithmic growth rate. So nt plus 1 over n is a minus bt, so exponential growth rate. So the statistical test, from looking at the data, and you have to massage the data a little bit to decide what is the starting point, what is time zero, which is usually a set in number of deaths that we've seen in terms of the coronavirus. You want to decide from the data whether b is equal to 0 or not. So either b is equal to 0 or b is positive. The null hypothesis is b is equal to 0, which means that you have exponential growth. The alternative hypothesis is b is positive, which means that you actually have some exponential. So can you do this statistical test, and what is the degree of confidence that you can get from the data? So we did all of this for all the states of the United States, and then many of the sub-states in India. I will not report all of the results, but we have those on our website. But it was interesting to see, and this is a picture of all the states in here in the United States. The blue curves indicate exponential, sub-exponential growth, which means that there is a flattening of the curve. So you look at a place like Arizona, a place like Maine, have all shown sub-exponential growth. But for example, if you look at Massachusetts, it didn't. And in fact, we're still seeing increases in the number of cases in multiple locations. California is, I believe, is the same situation. It has not stabilized. Virginia has not stabilized, and so forth. And this was a study that was done 10 days ago, and the prediction was usually about a short horizon after the data has been collected, right? So this is not a global model. These are short-term models. In fact, we actually also used the data to estimate the peak value, the apex, and that study was done April 17th, so it's very recent. So what we're doing, we're looking from the number of 80 deaths in the 80th day of the infection. So this is the starting point. How many days it takes for us to peak, and in fact, we see, for example, certain counties in California have actually already peaked with high confidence. Some counties haven't. You see Massachusetts over here, we have many counties that have not peaked yet. This is many days after the initial recordings, and so forth. And so we can estimate if you actually have reached a plateau. Reaching a plateau does not mean that you see a sub-exponential, which means that things can drop, but it doesn't mean that later on they won't come up, right? So these are local models, and of course, if you change a policy or you change a strategy when you can see another peak. But right now, assuming all the conditions are the same, we expect that once the peak is reached, you actually start decreasing. So these are valuable data that has actually confirmed a lot of the measurements that we've seen so far, and they use non-mechanistic models, simple sub-exponential models that I described earlier, and you use what we refer to as the noisy data, but in a particular way. And so the interesting question here is, when you think about intervention, do they actually matter and are they helpful? And that's an important question for us to understand. So that's the other piece, because intervention is going to be the way in which we can tackle a lot of these problems. And here I want to show you a study that we did about mobility, where we got the data from Google to try to understand whether mobility has actually impacted the exponential growth rate of the number of infected cases. In this study, we actually looked at the number of deaths, because we felt that data was a little bit more stable across the world, and we looked at the Google data across the world. So the questions in general in these kind of interventions that you ask is, well, if we employed a different severe policy, would things be better? Or if we actually relax the policy, would things be worse, right? So it's a counterfactual question from an economic perspective, and you're trying to ask what would have happened in that situation. And in general, we answer these questions through control groups. So you have a situation where you employ a policy and a control group where you don't employ the policy, and you compare But in these situations, there are no control groups. It's not an experiment that we're conducting. It's a real-life scenario. So as a result, you have to construct what's called a synthetic control group. And this is an area that has been growing in statistics and led by several people, at least at MIT and IDSS. There is a very simple explanation of how you do synthetic groups and a lot of details of how you make it work. But essentially, the way you think about it is we're doing this across countries. And so what you need to do is first pick a bunch of countries that you think implemented similar policies. So for example, if it's mobility restriction, did they restrict mobility by 10%, by up to 40%, or by up to 60%? And then you pick those classes of countries. You look at the pre-intervention data of infection or deaths, and then you regress one country on the data sets of the rest of these countries. So for example, we're trying to analyze the United States. We regress the United States data on the existing data of these other countries. And then we use the post-intervention data they had to project what the United States data would have looked like. Details of that is on the website. So the chain of kind of causality is that the policy restricts mobility, mobility restricts infection, infection restricts death. We need to understand the causal effect and understand exactly what would have happened if an implementation didn't happen. And the results are actually really amazing. So in the United States, initially, for example, there was we did not have restriction on mobility very rapidly, and you can see that the blue solid curve is the actual curve of growth of the number of deaths as the number of days after the 80th death, that was the 0th day, we see an exponential growth. Using the counterfactual argument and synthetic groups, it shows that if we employ 10 to 40% restriction in mobility, we would have been at the orange curve. And if we employed even more harsher mobility measures, we would have been at the green curve. And in fact, we use the counterfactual argument to cross-validate. So using the same technique, we actually predicted the actual data that we measured. So the dotted blue line is actually the prediction using the same techniques of what the data in the United States. So it's fairly robust sort of estimates that we're getting from here. Similar situation in the UK. And what is staggering and interesting about this is that the gap is actually huge. This implementation of going from only 10% to up to 40% can save a huge amount of number of people deaths, given the predictions that are given in this data. We've done this for Turkey, and Turkey implemented moderate restriction rates, and that actually came out also fairly accurate in the cross-validation. It shows, for example, if they didn't do that, an exponential growth rate that is much faster. Sweden is similar, although Sweden, the prediction, the cross-validation actually wasn't as accurate. And that has to do with the complication of Sweden in terms of what policies they're implementing, because they're actually implementing many policies at the same time, but they're all mild in nature. So yeah, the cross-validation gives us a sense of how good the estimates are. And finally, I will conclude here with India and the counterfactual. India actually implemented severe policy, and their growth rate is at the green line. The counterfactuals for moderate is orange, and then for none is the blue line. You can see the numbers. You can go up to 9 times the death rates if you simply did not implement the severe policy. There's an order of magnitude increase of the number of deaths had they not implemented this data. So we're trying to automate this particular methodology so that as we are experimenting with different tools and different policies going forward, we have a quick way of cross-validating and answering the counterfactual of whether or not that particular policy was effective. Particularly when you employ multiple policies at the same time, which one was most effective, right? And you don't want to murk the ground and have a lot of things going on. And so this stratifying methodology is allowing us to answer some of these questions. So that's the second piece of my talk that I wanted to communicate. So now I go to the part that has to remind us of control theory, and I call it itching to open as opposed to inching to open, because everybody wants to open. We are here in the United States dying to open, but we don't want to open because we're afraid that things are not going to go well. So we want to go back to normal, but we don't know what the normal is. So what is the new normal? And we're extensively thinking at MIT about MIT going back in the fall. Back in March, we were talking about the fall as a done deal. Now we're thinking about the fall, but we don't know. Are we going back in the fall or not? We will probably go back in some capacity, but it won't be the same as what we've done before. And the question is, what is that? And then for this community, why is this a control problem? What is the control problem here? I mean, from our community, everything's a control problem. But then why is this one a control problem? And this kind of tension between accurate models and ability to perform policy. And I think that this tension is really something that the control community has dabbled with for many, many years. The idea that we can actually implement control strategies without having accurate models. And the most important thing about control is that it tells you the direction in which you should move, not necessarily how much you should move, and you can adaptively figure out how much you should move. And I think this is the conceptual framework control theorists take, and I think that that's actually a powerful one in trying to understand this problem. I'm not saying one cannot derive accurate models, but we have to understand that whatever model we're fitting is varying potentially slowly as a function of the policies and as a function of many different parameters. And so adaptation is necessary in this game. The key variables that I think have finally reduced our thinking towards are three, in my opinion. It's testing, distancing, and quarantining. And these are all three actionable items. How and who you test, what is the distancing measure and how that affects your performance, and then your ability to quarantine. I think about this problem a little bit in a small microcosm of MIT or Cambridge. I'm not thinking about employing policies across the world. And I will make a few comments about how one can actually think about the larger problem. But when we sort of maybe think in a global way, but act in a local way right now. So as everything we do, we start with building models and trying to understand how infection happens. And in this particular case, we believe, at least as we think of a community like MIT, that we can build a detailed network model. So we will not just look at an aggregate SIR model, but we build a network model. And for an MIT community, say 10,000 students, 15,000 people, maybe every node can represent that person. Okay? So the question is, what does this particular network model look like? Well, I mean, people are interacting, and the network captures the infection rate. How? Well, in the number of people that you're connected to, and the probability of connection with several people. So these are many parameters that one can tune to reflect, for example, the value of R0. I can define that, and I'll come back to that in a minute. So the way you think about this is that every node carries a state. And part of the state is discrete, which is that are you susceptible, are you infected, have you been hospitalized, have you been recovered, are you been quarantined? There's a discrete state. There's a continuous state, which is your location, and that could be accurate or noisy, depending on the contact tracing methodologies that we have and how much has been adopted and how much has been allowed to be adopted by people. Some contact tracing self-report, and some contact tracing are using cell phone data to track you, and you get a lot of different sort of accuracy levels from those. But there's a state that describes where you are, and that's a continuous variable. And finally, there's a demographic that describes your age, your risk level, and maybe some information about you that is very helpful in describing this particular model. The graphical model now could be, from an analysis perspective, could be a random graph, dependent on the state. So, for example, if we're doing analysis, we can assume a Brownian motion or targeted Brownian motion, where people go to places and come back. For the synthesis, we need to track the actual positions and estimate the actual network from this data. So update a sort of a probabilistic model of this network based on the observation that we have. That's a large dimensional problem, it has an issue of dimensionality, but at some level or at some coarseness level, that can be done. So the state transition probability distribution is a function for the probability of infecting someone in your neighbors, depends on your state and their state and the distance between, the full state, both discrete and continuous, and you have to describe this particular model. This is a very complicated model. We're using it a lot for simulation. And of course, once you have a model, the first question is, well, what you can ask what if scenario, and there are quite a few what if scenario. So one of the researches that we have, the question that we were asking is, what if our policy just focused on quarantining the older community and then left everybody doing what they're doing? Okay, so kind of like the Swedish sort of model, quarantine the older community, separate them, and then see what happens. And so you can see a very quick comparison here. For example, if you have no intervention, it shows you the number of individuals who have been infected. This is the peak value for no intervention. This purple is quarantining the elderly, and of course the blue is the social distancing. So the blue is better. The purple is doing okay. It's not doing great, right? If you look at the hospitalization, all of a sudden now the purple is actually approaching the blue. That is, if you're just worried about hospitalization, quarantining the older community is actually effective in reducing the number of hospitalization based on this particular model. And finally, if you're controlling the number of deaths, actually quarantining the older community, completely isolating them away from the rest of the community, reduces the number of deaths. So it can start giving you a sort of a perspective of what's going on with this particular model. Assuming this model is fairly, have enough accuracy, the different policies have different impacts on different sectors that we're thinking about, right? And so this is one what if scenario. Another one which is really interesting is the herd immunity argument that people have been making, and the question of connectivity or R0, right? So the herd immunity argument is that, well, if you let the virus infect and we have a lot of people who are immune, then the transmission rate goes down, and as a result, we actually stabilize. And, one can argue that the Spanish flu, that's what happened. Ultimately, people developed immunity, and that's what happened, right? And so we actually did extensive simulations so on one axis is the value of R0, and the other axis is the immunity level. Of course, when the R0, again, I'll come back to this in a second, is the number of people that you infect during the time when you're sick, when you're infected, when you can infect people, right? So if R0 is equal to 1, you can only infect one person in the duration when you're sick. This is not a system that can grow exponentially, and actually it doesn't matter what the immunity level is, the probability of new epidemic is 0. It's very small. It's only when R0 is in the factor 2, now they're saying R0 maybe 2.5 to 4 are the estimates for this particular virus. Well, there is a level of immunity, say around 50% or 60%, depending on R0, where actually we can stabilize the growth in the epidemic. So the curve is actually, and if you look at this particular curve, the shape of the curve is really interesting. It looks like something like 1 minus 1 over R0. 1 minus 1 over R0. This is the shape of this curve. But that's not really surprising, so I'll come back to this in a minute. But this is what if scenario says, indeed, a certain level of immunity is enough to prevent the growth of the disease, and these models can give you a sense of the order of magnitude of how much immunity you actually need. Also justifying maybe doing some antibody testing. So I'm going to jump into the control problem and try to finish in the next 6-7 minutes. So the control problem for us is fairly straightforward. We're control engineers. The system is described in this. I call it the state. Essentially, it's the graph, the network that we describe. It's evolving dynamically. And what we can do is make measurements of this network and design a control strategy, right? What are the measurements? Well, the location measurements is something that everybody is looking for to try to get. But also some testing of infected people. And I want to emphasize here for the controls people is that testing can be divided into two types or two components. One that is random, you can randomly test everybody, but the other one is targeted. And I think of the targeted testing as a control variable because you decide who you test and then you go after them, right? So that's part of the control strategy that you decide. So the way we're going to think about it is you have some observations from this network over here. You build a predictor to give you on each one of the nodes, who has the highest probability of being infected, you apply some control strategy to either quarantine these people or change the R0 by social distancing. And then the system evolves. And so there's a prediction, there's a control, and then there's a feedback system that goes in. So that's kind of the idea of the control problem. Testing is huge. We're not going to be able to control if we don't have vaccination and we don't have a cure. Testing and quarantining is the only way we can control the infection, or unless we get to the herd immunity problem, right? So testing, you have to test high-risk people. You have to think of different strategy for testing people, right? So, for example, people that are more connected to others can have a higher possibility of getting infected and infecting other people, so they get priority testing. So there's a notion of centrality in people here, or page rank kind of an idea. There's also hotspots of location. People go to certain location. At MIT, students go to a classroom. Machine learning class has 600 students in it. That's a huge mixer, you know? So sampling randomly at that location is also one possibility of increasing the prediction for the disease. And the question from an optimal control perspective is really, what is the optimal prediction that we can come up with? You know, we have a model, we have some intuition in terms of the graph. What is the optimal prediction? Once you have that prediction and you have the ability to remove people, you actually have a very effective mechanism for control. And I'll describe that in a second. Then the second one is distancing, because if you cannot have enough testing, then that means that you have to actually reduce R0, reduce the number of people that you can infect that you are coming across. So in the graphical or the network model, that means that we reduce the number of people that you're connected to, or reduce the number of people that you interact with, okay? So in a simple argument, if you want to, as a control theorist, think of very simple parameters that you want to understand this trade-off in the control system, let's just sort of come up with this very simple idea. So remember, R0 is the number of people that one person can infect, until recovery, right? TR is the time of recovery for a particular patient. And then TF is the fraction of people that are being tested. And so that right now, let's think randomly, 5% of the people being tested, 10% being tested every day, 1% tested every day. And then IF is the fraction of people immune. So the first trade-off, you think about it, it comes from thinking of this problem as an MM1Q, right? So people are arriving to the system sick at a rate R0 divided by TR. This is how they arrive to the system. And if you're testing them at a rate TF, okay, then you're testing and removing them out of the system at a rate 1 over TF, okay? Then if this product is less than 1, you have a stable Q, and the Q would not grow in the size of the number of people, okay? So that's kind of a simple queuing theory argument. It's a worst case queuing argument. It's not I'm not taking the network into consideration. I'm just looking at it as a qualitative measure. Actually, people are leaving the network at a faster rate because also they're recovering. But let's just say, so this is one way to think about it, is that if R0 is 4, then the percentage of testing and quarantining has to be such that this product is less than or equal to 1. That's a coarse argument for how you conduct your test. If you don't have the capacity to test people at that particular rate, then you cannot stabilize that system. How immunity comes into the problem is that the fraction of people who are not immune multiply this, so they make the problem a lot bigger. So if you have 30% immunity, then it's only 70% of that matters, okay? Because the 30% will not be effective. If R0 is 2, it's really R0 times 70.7 that actually is the effective R0, because most, 30% of the people you encounter cannot be infected. So this is kind of where we're thinking in terms of the control strategy of this problem. And we have actually, now this is done, as I said, thinking of it as a simple queue, but in fact, you can do the simulations with this complicated model that I described to you earlier. But what the simulation is showing here is what happens for different values of R0 and fraction of testing and fraction of recovery the time for recovery. And what is interesting about this is that at 1, when this is the inverse fraction of what I showed, right? This is 1 over that quantity here. So when 1 over that quantity is greater than 1, the number of infected people stabilizes to a small number. So this is actually a stable system in this regime over here. And before that, well, it depends, right? For R naught being large, the infection is higher. For R naught small, the infection is smaller. And this sort of describes so you can see it in this graph over here. This is the fraction of how many people you test, okay? And so you can see that the more you test, of course, the more you stabilize, and you need to have that ratio greater than 1 for the stabilization of that system. So even the simulations with this complex model corroborate this particular idea. So we begin to think of testing in a systematic way. I'll skip that with the immunity. But finally, because I'm running out of time, I just want to say that random testing can get you so far, but targeted testing can do a lot better. And here's an example also simulated in terms of simulation of this particular model. If you look at no testing and the number of infected people, that's the red curve over here as a function of number of days. So we just simulated for a large number of days. If you actually do this centrality page rank, so this is the one where a person is tested because they have high probability of infecting other people because they have higher connectivity, higher centrality, page rank. Actually, this is a really effective measure. This is the same amount of testing that is allowed. So you get the blue line, which prevents the number of infection by quite a bit. The purple line is the random test, which is pretty good, okay? And the black line, the black curve is the one where you're testing the hotspots, okay? And it appears that in this particular simulation, at least, that the testing randomly is better than hotspots, but in fact, centrality is better than all of it. And of course, I believe that the optimal testing strategy is going to be a combination of the three: high centrality people, hotspots, and some random component that will actually see what's going on outside those systems. With optimal testing and optimal quarantining, I think what we have is a situation where we can be removing people from the system in time so that the system doesn't grow exponentially. And that's exactly the whole control strategy. As I said, absent of vaccination, absent of a cure, the only way to prevent growth is to prevent R naught from being greater than 1. And that's the way to do it, is to remove people from the system before they are able to infect other people. If your testing strategy or testing capability is not as frequent and you have more limitation, then of course we need to get into social distancing or physical distancing. And in a community like MIT, what does that mean for us? How do we go to labs and exercise physical distancing? We're doing quite a bit of work, at least in terms of understanding those components in the control problem. Finally, I didn't have time, and this is a separate conversation. There's obviously privacy and social considerations that we have to worry about, and economic considerations. Contact tracing is a huge issue in terms of privacy because you're tracking people everywhere they go and you have information about them, and so you need to be protecting their identity and so forth. But you can't be protecting their identity and going to test them, and so there's a question about how you do that. And social, ethical issues and economic issues. I mean, we recognize that while in fact it's safe to lock down has actually resulted in 130 million people starving in the world and an economic downturn and so forth. And I think that quickly coming with a solution that employs active control but allows us to operate under that active control is paramount for the sanity and the viability of our society. So I conclude very quickly by saying non-mechanistic models have been very helpful in understanding many parameters in terms of estimating trends, growth rates, sub-exponentials, and understanding actually the impact of intervention. None of these require detailed SIR models. All of them were done actually with simple kind of logarithmic exponential growth or logarithmic sort of exponents. But the SIR models provide different types of questions about what other strategies you can apply, and simulating them and analyzing them and give you a bit of information about how we can think about these things. Ultimately, I think that the ingredient for control is being able to test, distance, and quarantine. Based on the testing, and you can distance and quarantine people, you're actively controlling the growth in the system, and that actually is the way I would think about a control problem, helping us in that regard. finally, in terms of how do we deal with a massive, how do we deal with a state like Massachusetts or a city like Cambridge? I think, my proposal, and we're thinking quite a bit about that, is to think about functional decomposition of our society. We have people in schools, we have people in universities, we have construction workers, we have drivers, we have an election coming up. These functional things can be controlled as units because people do similar things in them. And then one way we have to think of an architecture of how we piece those functionality together, which I feel like is an interesting hierarchical type control strategy. And as I mentioned at the end, privacy concerns have to be dominating our analysis. So with that, I stop and thank you so much for your attention. And I went a few minutes over time.
Okay, thank you very much.
Thank you.
And
You want me to unshare?
we thank you very much, Munther, again. I think, as I told to Mario, the fact that the network plays an important role is something that we all have been thinking, and I think you gave us some nice insight in that direction. As I told you, I know it's a keynote, but I would like to have give space for some questions, so to chat a little bit together. So, Martina, you collected questions. Who?
Yes, we have a first question from Alessandro Rizzo. Please, Alessandro.
Hi, Munther. Very nice talk. Very interesting. I have just a question. How would you rank how would you page rank in practice, people?
So the way we've done it in the simulation is using the contact tracing.
Okay.
And so with the contact tracing, we built actually a directed graph, and so the directed graph indicates not only your location but where you were. So there's a node between me and you. If I came to a location that you were at within a certain time horizon.
So you are imagining a full contact tracing, like a full reconstruction of the network of contacts.
Which it's very expensive.
It's very invasive, quite invasive. I mean,
it's very invasive.
Nations are debating about it, but I mean, it's something to reason about it. Actually,
exactly right. I mean, the point is that this is what you can do with full-fledged information.
Sure.
Now the question, maybe we can have partial information, or I can get a distribution, and then from the distribution extrapolate the people that we have. And I think you're absolutely right. We need to kind of figure out all of these scenarios.
Yeah, but it's okay. I mean, starting from ideal conditions and then figuring out what we are missing, it's anyway a clever approach. It's very interesting, though. Thank you. Thank you very much.
Yeah, thanks.
Other questions?
So, yeah, we have another question from Bob.
Thank you, Munther. I enjoyed that. It's a comment, really asking you for a comment. And the testing process is, we treat it as a sensor, and control systems people are not very good at deciding when to put their effort into designing better sensors. And so the Icelandic example is interesting from a kind of convincing sense of convincing politicians, for example, that if you spend a lot of money on testing early, your economic performance later is going to be a whole lot better. And as control people, we don't grasp that well enough. Medical people do. So they know that if they do what's called point of care testing, which is testing people, not for COVID, but things like hepatitis B, you spend money on cheap but very early broad testing versus waiting for sick people to turn up and get tested. You can save a lot of money and in morbidity and mortality. The signal processing people, in radar, for example, and the military guys, they have expensive radars, fantastic capabilities. They don't dare turn them on because then the enemy will learn what the capability is.
Right.
We're kind of in that situation where it's not just control; it's also getting to grips with the cost of sensing.
Yeah. No, it's a great comment, and I think that I think we're coming around. Is my answer as control people that investing in sensing is like investing in actuation, and we take sensing for granted when we build engineered systems because we decide where to put these sensors ahead of time, and then we're done. Here, it's a dynamic process. It's an ongoing decision process, and the way I think of it is that you have a fixed resource and you're trying to allocate that resource. If I had infinite sensing, I'd sense everybody every day. Of course, not possible. I have a fixed resource and I need to allocate this resource. So what is the optimal allocation for the objective of preventing reinfection or an increase in the virus? So it does fit into the control mentality, but you're right. Now, this has a cost or a constraint, and it's actively selected. So not everybody is being sensed all the time. You're deciding who to sense all the way at every step. It's a beautiful control problem, and I think once we have time and this virus is gone, maybe we'll develop some theory to solve it as well. Yeah. But I think what I'm saying is that also a lot of people are thinking about optimality right now, and what's the best way. Granted, I think as we're helping MIT come back to campus, we're going to come up with feasible solutions quicker than what the exact optimal solution is. But I agree with you. This is a beautiful direction for control theories to think about. Yeah.
Thanks. So, Martina, I will leave another quick question since we are getting a very nice chat.
Last question from Robert.
Yeah, I just had I was just curious as to what your thoughts are on the level of testing that's required. It would seem to me that there's two different situations. There's a situation where the fires are just starting, where you've got very localized hotspots, but where you have small fires in the community that's very well mixed, then it would seem to me for that latter situation, which is probably what we have right now, the level of testing that would be required to quarantine enough people to mitigate the virus would be almost prohibitively high. And the reason I'm saying that is because if you look at the narrative from politicians all over the world, they see testing and contact tracing as the way out of this. And I'm not sure, to be honest, that it is.
So I, for example, we did some calculations, and hopefully we'll be posting a lot of that stuff in the next few days on our website. So, for example, we did some analysis for the MIT community. Sorry. For the MIT community, which is a smaller but has these hotspots. And we came up with about 20% testing on a regular basis. Well, it's non-trivial. I mean, that's not 1% or 2%. That's a lot of testing.
Yeah.
We were told that MIT can have that capability. So we can test regularly every day. Of course, as I didn't mention this, but testing that's the way it's happening in South Korea and China is also not just testing for the virus. You can do the first responders testing, like do you have a fever, or so there are things that you can read out of cases with reasonably high probability of error, but still taking out many people out of the system right away, right? 20% is high, but 20% we have the capability to do it actually daily, to test 20% of the people and get the results in time. But if all of these people, a good percentage of these people need to be quarantined, then we cannot do that. Mm-hmm. So hopefully we get to this problem before we are testing and quarantining. We're testing and quarantining the very first few people that prevent our not being free, that stabilizes the system. So we got to get to this problem early, take out the people who are infectious so that the growth is not exponential. And then that's actually the manageable problem. But it's a great question of the resources that are needed to do the right thing, and quantifying these resources is a great thing to provide for the policymakers.
Yeah,
a simple graph would be important for the policymakers.
20% is consistent with the numbers that we've been seeing as well. I'm not sure that's really feasible at a national level to be testing 20% of the population every day. And don't forget, these tests are very invasive. They're not simple tests.
But remember, you could impose some social distancing or physical distancing, and then go with less testing. So these are trade-offs.
Yeah.
You know, you want to go back to normal life, you need about 20%. But if you want to go to a new normal, but you're still working, you may be testing 10%. And I think we need to your point, I think we need those trade-off curves and the price next to them, so that, you know, kind of in an aggregate way, so policymakers can think about what strategies to follow.
Nice. Thank you again. It was really nice. And let's try to give another applause. Virtual. Okay.
For the invitation, and I hope you have feedback for us. Just visit our website and post on it.
Perfect. Perfect.